Yesterday, we talked about the types of bonds, your single, your double, your triple bonds. We know that every bond is two shared electrons, one from each of the elements. When they form a shared pair, that is the bond. So we can use a line to represent two electrons, or we can use dots. Don't care which way you do it. We talked about our diatomic molecules. We talked about how they form their bonds based on how many unshared electrons each one of them have. When we got to our oxygen, we got our nice little smiley face double replacement, or excuse me, double bond. We got our triple bond for our nitrogen. When we're doing our molecules, we're starting to understand that if we have the lone pairs on the central atom on the same side, that repulsion is going to cause it to create new bonds altogether. When those new, well, not new bonds, but new shapes, the new shapes will actually push it to be in the shape that we're going to call it. So the lone pairs on the same side is pushing everything down so that we have an equidistant bond angle between each of them. And that's what gives each of these molecules their shape. When we're looking at the beryllium and the hydrogen, we're going to have some of these on here because it'll actually show up pretty easy, even though this is not going to have access to 8. These are the special ones. We're not going to do them very often, but there's a couple on there just because it's special and you should be able to figure out which ones are special. Are exceptions to the octet rule: hydrogen, lithium, beryllium, boron. Hydrogen, lithium, and beryllium all can only have access to 2 electrons when they become ions at the most, or when they form their bonds. Because of that, they're not going to ever get to that octet. That's all they're saying is it's not going to get to 8. Okay, I'm going to leave this one here for a couple seconds so you get, or a couple little bits so you can go ahead and copy it down. Notice that the first element is the central element. Why? Because the central element has the most unshared electrons. That means it'll be the one that will have the most bonds that it can form. The element with the most bonds that form will be the ones that's in the middle. Once you have put them around, made your bonds, then you're going to put the remaining pairs around the outer elements until every element has access to 8 electrons. SO4 with a 2 minus, you'll notice that there's extra electrons there. We put these in brackets when we're showing this so that we can show that there has to be 2 extra electrons in order to have this configuration. As you're using this, you can pause it and get what you need off of each page. I'm going a little fast because I don't have a lot of time to get all of this in. If you notice, it doesn't matter which one gets the double bond, but only one of the oxygens will have a double bond with the carbon. Okay, resonance. Multiple electron dot structures can be written, meaning there's multiple different ways you can write it. That's like what we just saw. On our 3D structures of covalent molecules, this is called VSEPR theory. Valence electrons will determine the shape of the molecules. The structure of the compound is based on electron pairs repelling. The molecules adjust the shape so the valence electrons are the farthest apart. VSEPR stands for valence shell electron pair repulsion theory. Essentially, we're saying that areas of electron density have all got the same charge of negative, and because they're all the same, like charges will repulse each other, and that's what determines the shape of these molecules. If I have one central atom with 4 elements surrounding it, That is going to be called a tetrahedral shape. It has a bond angle of 109 degrees. The reason is it's not on a plane, on one single plane. This is on a 3D plane. So this is not just a carbon with 4 hydrogens surrounding it. They're in different angles. The angle between each of the hydrogens would be 109 degrees. In the ammonia example, called a trigonal pyramidal, we have 3 elements connecting to the central element with a lone pair. The lone pair being farther away is not going to apply as much of a pressure on it. So the distance is not going to be 109, it's going to only be 107. What will happen is this will look kind of like a pyramid on the table. Water is known as a bent molecule. There are 2 types of bent molecules. One is if you have a single lone pair on the central atom, and one is if you have a double lone pair. Their bond angles will be different for each one. With the single lone pair, you usually have a bond angle of around 109.5 to 109. With the 2 lone pairs, you have 104.5 to 105, or we round it to 105. Carbon dioxide is a linear uh, type of compound. Understand that in order for it to have a bond angle, there has to be 3 points. If I have just 2 points, it's just a line, there's no bond angle. Boron only has 3 valence electrons. It's a special substance. It tends to form special shapes all the time. It has a higher bond angle. It will tend to only have the 3 elements around it. Since it only has 3 elements around it, the repulsion is going to be equal in all areas, so it forms on a single plane. So this is basically, if you are familiar with like Chinese throwing stars, this is what it would look like. It's all on a single plane, 3 points out in the same, or if you wish, a fidget spinner. This looks a lot like a fidget spinner. It's all on the same plane. See what you can do for a challenge here. How many of you can do this phosphorus pentafluoride? And finally, try to do a sulfur hexafluoride, which is an octahedral shape.